Hi everybody, welcome to another IZ8 DWF arcade repair video. Here I've got an Atari Super Bug PCB that has been sent for repair. This board looks very nice and clean indeed. Super Bug is a card game made by Key Games, an Atari company, in 1977. So this is, as of today, the oldest arcade game I've ever seen on my bench. It seems this is a second revision Super Bug PCB, if that handwritten number is indeed 02 as it looks like. In fact, we can find some bodge wires installed from factory. Here are some more wires, for example. By the way, like most PCBs of that era, it doesn't have solder mask on the component side. Here we see a missing quartz crystal, so I need to find a replacement for it. And this component is completely unsoldered. The unsoldered component is a silicon-controlled rectifier that's used to turn on an incandescent lamp under a button, and the original component is not shorted or otherwise faulty. So I've just soldered it back in its place, and of course I've checked all other semiconductors and capacitors, as I always do on these old boards. The quartz crystal needs to be cut for 12.096 MHz, and I didn't find any suitable one in my spare parts. So, while waiting for the new crystal to arrive, I've decided to inspect all the bottom side of the PCB for broken or suspicious solder joints, and that was a really good idea, because I found quite a few bad joints even under the main CPU socket. Then the replacement crystal was finally delivered, so the board is ready to be connected and powered on. Wiring these old game PCBs is usually a bit complicated. I've shown why this happens with much more details in the Atari Avalanche clone video, which is linked down in the description. One of the reasons why I used a few AC transformers is because it expects a center tapped 25 volts AC supply, then a 6 volt AC supply for the incandescent lamps, and last a DC supply for the onboard 5 volt regulator. Notice also the presence of this big 20 watts resistor. I'll show why it's needed later in this video. Then we also need to connect a couple of switches normally closed to ground for the CON inputs and a toggle switch for the test mode input. The game needs a quadrature encoder for the steering wheel, so I've connected one encoder output of an old mouse for it. One button of the mouse has been connected as the gas pedal input. And last, we need a 4-way switch for the gear lever, and I've wired a suitable rotary switch for it. Of course, the first thing to check is the correct 5 volt regulated output, and luckily that's okay. Well, the board started fine, it's running the attract mode. Of course, I need to test that every control works as expected. So let's try the first coin switch. Looks good, the start lamp is now blinking. Now I reset the board so it stopped blinking, and let's try the other coin switch. Yes, now it blinks again. Now let's try the track difficulty lamp. Let's coin the game first. Then contact the difficulty switch wire. And yes, the other lamp is now on. If I contact the switch again, the lamp turns off. So far so good. Finally, if I contact the start button, we hear the motor sound. On many old games and devices, we can often see a low ohm and high voltage resistor across a linear voltage regulator. In this case, the regulator is an LM323, and R61 is a 2 ohm resistor bridging its input and output terminals. The resistor is rated for a whopping power of 20 watts. The LM323 is rated at 3A output current and 30W power dissipation, but these ratings were probably not enough for this board current consumption. With this game original power supply, the DC input to the board would be approximately 11 volts, since it's rectified with a center-tapped full-wave circuit. If there was no bypass resistor and with only 2A of load current, the regulator would dissipate already 12 watts, but for sure the current requirement of this board is higher than 3A. In fact, with 11 volts input, R61 passes 3A to the 5V rail and dissipates 18 watts in form of heat. The regulation only works because the actual current requirement for the 5V rail is a bit higher than 3A, otherwise the regulator would not be able to keep the correct rail voltage. With the 9V DC supply that I'm using, however, the resistor only passes 2A to the load and dissipates 8 watts. After 10 minutes of continuous operation, the resistor external surface got already very hot, more than 93 degrees Celsius. The regulator heatsink is, however, able to dissipate the heat more effectively and only reached 55 degrees Celsius. Out of curiosity, I tried to measure the temperature inside the ceramic cavity of the power resistor. That's almost 135 degrees. Imagine what we get with the original power supply of about 11 volts. However, these resistors are rugged enough to withstand these temperatures, but you don't want to touch them if the board is powered on. The reason why this PCB needs more than 3A on the 5V rail is because almost all logic ICs are from the old 7040TL family. There is not even a single 74LS family member. The LS family is a low-power version of the original 7040TL, by the way. I found at least one 74S chip, but this has about the same power consumption of the regular 74 It is just a lot faster. Then a few other ICs are member of the 8T TTL family, and these actually are very similar to the 74LS bus transceivers, but 2 or 3 of them among all the others don't make any real difference. And just for the record, this is the IC with the earliest date code I could find on this game PCB. It was made in April 1976 and probably in Germany. All the original ICs on this board appear to be still in good working conditions. So I tested all inputs and they worked fine, and it's time now to try to play a game. It's, however, very difficult without the proper control panel. And I think this is still a nice game despite its age. So it's all for this video. I hope it was interesting and that you learned something. If you have any question, use the comment section below. Have a nice time and thank you for watching.